I'm about to tell you 3 things about magnetic fields that I'm guessing, I'm just throwing this out here, that you probably didn't know. And these are like 3 surprising tricks of magnetic fields. Trick number 1. How can a black hole, black holes, how can a black hole have a magnetic field? Black holes, the very definition of a black hole is that nothing can come out, not even light, which is electromagnetic radiation. So how can a black hole have a magnetic field if nothing can come out? Well, here's the thing. This is the exact same question as asking, how can a black hole have mass? How can a black hole emanate the force of gravity if nothing can come out of the black hole? How can a black hole emanate the force of magnetism if nothing can come out of the black hole? Here's the thing. When you're in the vicinity of a black hole and you're feeling its mass and you're feeling its magnetic field, you're not feeling the mass or magnetic field of the black hole itself. You're feeling the mass and the magnetic field of the ghost of its parent star. Remember what happens when you fall into a black hole? If you were to fall into a black hole, you would just sail through the event horizon, then you would die horribly, blah, 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 and it's all hilarious. But me watching you fall into the black hole sees a different picture. I never get to watch you cross the event horizon, that boundary, that point of no return. You never cross it from my perspective. You just approach it, and you get slower and slower and slower, more and more redshifted, slower and slower, more and more redshifted. I never see you actually cross. This is the exact same thing that happens to the star itself that becomes a black hole. Once that event horizon forms, there is material falling in, continuing to fall in, and it does fall in. The black hole grows, everything, but from our perspective, it appears glued onto the surface. It appears glued onto the surface, and it still has an effect on the outside world because it's not through the black hole yet. And we feel the mass, that shadow of the dead star. We feel its magnetic field because that star was made of charges, electric charges that were spinning around really fast, had a great magnetic field. That magnetic field persists to the present day. This is one of the consequences of this weird thing where special relativity and general relativity tell you that different observers have different perspectives. One of the extreme examples of this is around a black hole. Now, the second weird thing about magnetic fields is, this isn't the surprising part, that there's no such thing as a north magnetic pole or a south magnetic pole by itself. If you have a magnet, you get north and south together. You chop that thing in half. You don't get a north pole over here and a south pole over here. You just get a tiny north-south thing magnet over here and a tiny north-south magnet over here. You keep chopping it up. You just keep making these pairs of north and south. There is no reason why our universe can't have isolated magnetic charges, what we call the monopoles, a single north pole, a single south pole. There's nothing forbidding it in our universe. We simply don't observe it. And we haven't observed it for so long that it's baked into our equations of electromagnetism itself. They just state no magnetic monopoles in our universe. But that's like an assumption based on observation. So all the magnetic fields that we see in the universe are generated by moving charges, not by having a monopole existing independently. But something interesting happens if there was at least one magnetic monopole in our universe. Just one. If you were to just play the mind game, this is just a thought experiment. Let's just have fun. This was first cooked up by Paul Dirac, one of the founders of quantum mechanics. He was looking at a system and playing around and say, okay, let's say you have a magnetic monopole, a north charge right there. And then you bring around an electric charge, say a positive charge right here. He asks, what do they do? Turns out they start orbiting around each other. They start spinning. There is an angular momentum associated with that system, momentum going in a circle. That's no big deal. What he found surprising is that this effect doesn't matter. with how far away these particles are. They could be over here and they'll rotate. They could be like this, out of frame of my camera, and they'll do this. They could be on the other side of the Milky Way galaxy. Same deal. Okay, that's kind of cool. But we know from quantum mechanics that angular momentum is quantized. Angular momentum going in a circle, comes in discrete chunks. You can only have one package of angular momentum, or two packages, or 3 or 4 or 5 million, and 5 million and 1 and 5 million and 2. You can't have 5 million and a half. You can't have 6 3/4. You can't have, I'm sure you can imagine other fractions. You can't have fractions of this fundamental unit of angular momentum, which we call Planck's constant. So these two particles, the north charge and the positive charge, orbit each other. There is angular momentum there, a fundamental limit to the angular momentum due to the quantization of nature itself. This means that the electric charge must also be quantized. This is an explanation for why electric charge is also quantized in our universe. You can only have one unit of electric charge, or 2, or 3, or 5 dozen. You can't have half. You can't have 3/4. And I'm ignoring the quarks for now. If you're interested in the physics of quarks, that's another episode. But it's the exact same argument applies. Electric charge in our universe is quantized, comes in discrete packets. Again, there is no explanation for that. There's no reason for that. We simply observe it in nature. But if just one magnetic monopole existed in our universe, that would be the reason for the quantization of electric charge, which that's a pretty powerful trick. But that's not all. Magnetic fields have 3 surprising properties. I've only got 2. Here's the last one. If you take a charge, an electric charge, it has an electric field, and you're really bored. What if you start running by it, though? What if you start, chugging along, boom, 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 and you're watching it, all right? From your perspective, you're not the one who's moving. Everything else in the universe is the one that's doing the moving, right? So from your perspective, you're staying still, and the electric charge is doing this. But what do moving electric charges do? They create magnetic fields. So if you're staying still, you see an electric field. If you're moving, you see a magnetic field. Are you looking at fundamentally an electric field or a magnetic field? Yes. You're looking at both at the same time. It is impossible to think of electric fields and magnetic fields as being separate things. They must be united under a common framework that we call electromagnetism, as discovered by James Clerk Maxwell in the mid-1800s. What does this sound like? Two things that appear to be different but are really just two sides of the same interwoven coin. Does this sound like space-time? Does this sound like energy and mass? I hope it does, because it's supposed to. Because electricity and magnetism were the precursor for special relativity. They were the precursor for special relativity. I almost said general relativity. General relativity comes from special relativity, so I wasn't technically wrong, but just slightly confusing. So I'm going to leave it in. I'm not going to even edit that out. The unity of electricity and magnetism led Albert Einstein to figure out special relativity. It was through his examination of the interlocking nature of electricity and magnetism that he was able to uncover the connectedness between space and time and energy and mass and all of special relativity. So it's thanks to magnetic fields. It's thanks to magnetic fields and the impossibility of separating them from electric fields and considering them as separate things that we have a cornerstone of modern physics. So there you go. Magnetic fields. They led us down the road of special relativity. They have some surprising and possibly very interesting explanations for a fundamental charge on the electron, and they can come out of a black hole even though nothing can come out of a black hole. So there you go. 3 things. 3 reasons why magnetic fields are the best fields. Thank you so much. I hope you enjoyed this video. Don't forget to like and subscribe and make sure notifications are turned on so you know when I come live. And you can go to patreon.com/pmsutter. There's a link here. Let's say it's over there. I don't really remember, where you can help keep these videos coming. Thanks so much for watching.